The following program is brought to you by Caltech.
Good morning, everyone, and welcome to the 2011 Caltech Space Challenge. My name is John Mahaley, and this is the first lecture in the lecture series sponsored by Lockheed Martin. And this morning I have the pleasure of introducing Dr. Donald Yeomans, who is a senior scientist at JPL and the manager of NASA's Near-Earth Object Program. And today he'll be talking to us on why we should go to a near-Earth object. Don?
Good morning. When I was driving in this morning, I was listening to NPR, and there was John talking about this conference. So you folks haven't even started, and you've got national interest already. Can't do much better than that. I'm going to talk to you a little bit about near-Earth objects. I mean, why bother? Who cares? So at the end of this, I hope you'll all care deeply. All right, the first item when you talk about near-Earth objects is science. It is an artist's conception of what the solar system might have looked like 4.5 billion years ago when it was forming. In the inner solar system, you've got the rocky bodies agglomerating to form the inner planets, Mercury, Venus, Earth, Mars. In the outer solar system, you've got the rocky and icy bodies agglomerating to form the giant planets, Jupiter, Saturn, Uranus, and Neptune. And the leftover bits and pieces from this formation process are what we call asteroids in the inner solar system and comets in the outer solar system. So if you wish to study the chemical mix and the thermal environment under which our solar system formed 4.5 billion years ago, you'd like to study these primitive bodies called comets and asteroids. So that's one of the science goals. Here's a 30-second summary of the solar system. It's been smushed together so you can see it all. So you can see that the asteroid belt is located between the orbits of Mars and Jupiter, and in fact, the reason that the asteroids in that belt didn't form their own planet is because Jupiter formed rapidly and first and frustrated the formation of the bits and pieces in the asteroid belt. So were it not for Jupiter, there would be another planet between Mars and that location. So the asteroids formed there. The comets formed out here in the so-called Kuiper Belt region and scattered disk region, and they are most of them were then thrown out into the outer edges of the solar system at about 100,000 astronomical units, one astronomical unit being the distance between the sun and the Earth. So they form, the comets are at the very edge of the solar system where the sun can barely hold them gravitationally. So outer solar system comets, inner solar system asteroids. All right, when the Earth was forming, it was drawing to itself most of the material in its neighborhood as it went around the sun. So initially it was very hot, and oceans could not have survived. And either could organic materials, carbon-based materials. So those are the two major building blocks of life. So you have to ask the question, if the Earth was so hot, how on earth did it get a veneer of water and carbon-based materials that allowed life to form? Well, one answer is certainly the comets and asteroids in the near-Earth neighborhood brought to the early Earth much of the water and the carbon-based materials that allowed life to form. Another reason why they're so important. After life did form, subsequent collisions, the level of collisions decreased substantially after the so-called late heavy bombardment 3.9 billion years ago. But still, there was major impacts from time to time, and they caused mass extinction events from time to time, one of them being the so-called Cretaceous Tertiary event that occurred 65 million years ago that wiped out the dinosaurs and much of the other species then on Earth. There are alternate explanations for the death of the dinosaurs, of course. Some scientists believe it was a period of very high volcanic activity. In fact, the the Deccan Traps in India is a very large lava plain, and some folks think that those volcanoes contributed considerably to the death of the dinosaurs some 65 million years ago. There are additional alternate theories, change of diet. My favorite alternate theory, however, is this one. All right. Another reason why comets and asteroids in near-Earth space are important is that they may well provide the raw materials for building space structures in the future. Future habitats will require raw materials that are already there. It costs around $10,000 to raise a pound of material from the Earth's surface to low Earth orbit. So if you're going to build a structure and a habitat in space and stay there, you're going to look around for raw materials that are already there. And comets and asteroids are the easiest, or some asteroids are the easiest objects to get to in terms of fuel, or delta V, as they call it. Even easier than the moon. Asteroids have far richer resources of minerals and metals than do the Earth or the moon. The reason there is that the Earth, after it formed, had plenty of valuable minerals and metals, but it differentiated, it formed layers, and most of those, most of the valuable minerals sunk into the core region. And of course, that didn't happen with the asteroids. Water is available in comets in the form of water ice. In fact, about a third, comets are made up about a third water ice, other ices, silicate dust, clumps of material. Water is also available in some asteroids in the form of ice and hydrated minerals. And water can be broken down into hydrogen and oxygen, which is the most efficient form of rocket fuel. So in some sense, comets and asteroids may be the future fueling stations and watering holes for interplanetary travel. Then, of course, we've got to find them before they find us. The issue with near-Earth objects running into the Earth is one that claims a lot of press. It usually gets the major portion of the press materials, but I mean, the events are rare, but of such high consequence that they do merit our attention. For example, a kilometer-sized object, and there are about 1,000 of them in near-Earth space, would not be expected to hit the Earth but every 700,000 years. But if it did, it would be a global problem, and it would wipe out a fair fraction, about a third of the Earth's population. So I don't know of another disaster that can claim that kind of damage. So it's worth our while to find these objects, monitor their motions, and predict where they'll be in the next 100, 200 years. And that's our job at the Jet Propulsion Laboratory, is to do just that in our Near-Earth Object Program Office. Now, NASA's vision for human exploration, President Obama stated this in April of last year, saying that by 2025, NASA should plan to send a human exploration mission to an asteroid as a stepping stone for the ultimate exploration of Mars. Now, Mars is the ultimate goal, but it's so tough to get there. I mean, you can only launch every couple of years, and it takes, 9 months to get there and 9 months to get back. So it's a long flight time out and back. And before trying something that difficult, you might want to try something closer to home, and asteroids would make a perfect example of a stepping stone to Mars. So you would test your technologies at something much easier than going to Mars or Phobos and Deimos. Test your technologies and the ability of astronauts to work together for extended periods of time at an asteroid, and then build on that for the human exploration of Mars. And then the benefits of the near-Earth object missions, of course, are research into the origin of the solar system, astrobiology. In some sense, we owe our very existence and our position atop the food chain to these objects that brought to the early Earth the water and carbon-based materials, and then punctuated evolution, allowing only the most adaptable species, that would be us, to rise to the top of the food chain. So they're not just whirling rocks and dirty ice balls in space. They're extremely important for our origins and our future. The future, of course, is the space resources. I mentioned that we have to test the technologies for human exploration, and we have to characterize the potential threats for the group of near-Earth objects that do, in fact, get very close to Earth. It's ironic that the objects that are in Earth-like orbits are the ones that are easiest to get to in terms of spacecraft, and they are the most dangerous in terms of the frequency with which they run into the Earth. So you've got this strange irony that these near-Earth objects are at the same time offer great potential for human exploration and mining, and also they represent significant threats. So we really do have to keep an eye on them and monitor their motions. The near-Earth object population is made up of comets and asteroids. I'm going to talk a little bit about comets, but because they're outnumbered 100 to 1 by asteroids in near-Earth space, I'm only going to mention them briefly. So the typical comet is a bit of a show-off. It's got a dirty ice nucleus. It gets near the sun. The ice is mostly water ice, carbon dioxide, carbon monoxide, ammonia, methane ices in varying degrees, but mostly water ice. So you get in within 3 astronomical units of the sun, and these ices start vaporizing, throwing off the entrained dust particles. The dust particles are blown back in an anti-solar direction by the pressure of sunlight. The gas is ionized and thrown back in the anti-solar direction by charge exchange with the solar wind particles. So these are the cometary nuclei that have been visited by spacecraft. Temple 1 up there at the top was visited and run into by the Deep Impact spacecraft. Borrelly, which seems to look like an old sneaker, was visited by the Deep Space 1 spacecraft. Wilt 2, visited by the Stardust spacecraft. Comet Halley, back in March of 1986, was visited by the Giotto spacecraft from the European Space Agency. And most recently, we visited Hartley 2, which is really a tiny little comet, about a kilometer from end to end. And it's strange because it's got 2 rough segments joined by a smooth area. And on the ends, it's carbon dioxide that's driving off icy water ice grains that then vaporize in the atmosphere surrounding this comet. So you've got carbon dioxide ices, dry ice, blowing off pure water ice particles, micron-sized particles, and they then vaporize in the atmosphere. This region is probably a gravity-low material that comes up, comes back, and preferentially sits down there. I'm going to show you just a couple of images from the Deep Impact mission, which I think was the mission that really advanced our knowledge of the cometary nucleus more than any other. It was launched in December of 2004, impacted on July 4th, of course, 2005. And it released an impactor 24 hours prior to impact. And so the impactor went in and hit the nucleus of the comet while the mother spacecraft that had released the impactor flew past and observed the impact. So the next image you'll see is the nucleus of the comet as seen by the impactor just prior to the impact itself. Toward the end, it got hit with some particles, and the attitude started jiggling, so the images were not quite as clear as they might have been. And then, of course, it vaporized itself at 10 kilometers per second. But it sent all that information to the mother spacecraft, which radioed it back to Earth, and so we have a pretty good understanding of what happened. There's 3 things that could have happened. We could have missed entirely. And I was doing the play-by-play for NASA television at the time, and that was one option I didn't want to deal with. Dr. Yeomans, you spent $400 million on a mission and you missed? That was something I didn't want to deal with. The other option was that the spacecraft could have buried itself in the nucleus of the comet sort of like a BB going into the styrofoam beer cooler and just absorbed it with just a, and that would have been interesting scientifically, but tough to explain to the public what happened. But what happened was that it hit exactly, well, within 100 yards of where we aimed it, and the micron-sized dust particles, which cover the nucleus to a layer about like that, those micron-sized dust particles blew up and made this impressive image here. That was the good news. The bad news is that cloud of dust also masked the crater, which is what we hope to see. Fortunately, the Stardust spacecraft, after going past Wilt 2, went on to fly by Tempel 1 and saw the crater formed by the Deep Impact spacecraft earlier. And what it turned out to be was a very indistinct crater. I mean, you imagine most impact craters being bowl-like. I don't know if you've ever seen Meteor Crater in Arizona, but it's sort of a bowl-shaped arrangement. But when they looked at the crater from this comet, it was more of an indistinct crater of a jumble of material. And I think the proper analogy there is that had this been a solid object, you would have in fact got a bowl-shaped crater, but it was a bit like hitting a pile of sand with a sledgehammer. You just get an indentation, and that, I mean, these things are porous to a level of 60%, so you're dealing with, and sand is porous to a level of 40%. So these things are about as close to a fragile object as you'll find. So from the imaging, we note from this comet that it has large, smooth, young surfaces. The smooth surfaces are young. The cratered surfaces down at the bottom, where we actually hit it, are ancient. And so these, what's probably going on is that this smooth area are ices that are retreating, a retreating scarp, and they are revealing the much older subsurface layers underneath. There's evidence of layering. Its effective radius is about 3 kilometers. The bulk density is 0.4 grams per cubic centimeter. Recall that water is 1, so, I mean, if you had a bowl large enough, this thing would float. So the porosity is larger than 70%, which is extraordinary. These things are very fragile, very friable objects. The albedo is about 4%, blacker than charcoal. The crater development took all of 5 minutes, which implies a very weak structure. And the vast majority of the ices, water ice mostly, are well below the surface. All right, so those are the summary of comets. And I mentioned that because comets form about 10% of the near-Earth object population, or X-comets could form 10% of the near-Earth object population. So this is a cartoon of why asteroids are so diverse. On the upper left, you've got perhaps a silicate object. On the lower left, you've got a differentiated or layered object with a mantle and core. They run into each other and form all kinds of objects. You've got silicate rocks, which is primarily what you're dealing with in the inner asteroid belt and in the near-Earth object population as well. But you've also got objects that are solid iron, nickel iron. You've got objects that are silicates. You've got objects that are rubble piles. You've got extreme diversity of asteroids in the near-Earth object population, far more diverse than we once thought. This is an interesting plot by Al Harris. It plots the rotation period of the near-Earth objects versus diameter. So as you get to smaller and smaller objects, the spin rate gets faster and faster. That's something you're going to have to keep in mind. The small ones, and you're going to be dealing with mostly small ones, tend to rotate rather quickly. And some of them would be a challenge to land upon. Possibly you can land on the pole to mitigate that. But notice this rubble pile spin barrier here. This suggests, although it doesn't prove, that the vast majority of asteroids are what we call rubble piles that are held together by little more than their own self-gravity. They do have some strength. There are van der Waals forces that are in operation. And they do have some gravity that's compacting them. But if they rotate fast enough, say 2 hours or faster, then they tend to fly apart. And so you don't have any objects up here. They're all down here. So this suggests that the vast majority of near-Earth objects are indeed rubble piles. It doesn't prove it, but it suggests it. All right, how do we know that there are iron asteroids out there? Well, Meteor Crater near Winslow, Arizona. It's 1.2 kilometers end to end. And the reason I know it's made of, or was caused by a 30-meter size or a 50-meter sized slab of nickel iron some 50,000 years ago is that I had a buddy who used to travel around the rim of this crater in a Jeep with a permanent magnet on the back, and it would just ride around picking up all of these meteorites, and he had an enormous collection of these iron nickel meteorites. Of course, this was private property, and what he was doing was illegal, but maybe the statute of limitations has probably run out, and he's reasonably safe. Okay, so here's a lineup of some of the more interesting asteroids. Mathilde, that was visited by the NEAR spacecraft en route to Eros, which was a near-Earth object. Earlier, the Galileo spacecraft flew by Gaspra and Ida and its tiny little moon, Ida. 15% of all near-Earth asteroids have moons. That's something you might want to deal with. A couple of them have 2 moons. Is that a benefit, or is that a problem for a visit by a robotic or human exploration spacecraft? Oh, here's my favorite image. This is the flyby of Mathilde. I find this fascinating. You've got 3 or 4, let me back this up. You've got 3 or 4 craters whose radii are larger than the radius, whose diameters are larger than the radius of the object itself. So if you get hit with something that big, how do you survive? Well, I can remember in the flight room when we were doing the analysis of this object, I was supposed to be the guy who, on the head of the radio science team, and our job was to determine the mass of this thing, because when the spacecraft goes by, of course, the deflection of the spacecraft, as a result of the nearby asteroid, you can measure that and determine the mass of the object because you know the distance and you know the deflection. And so we determined the mass, and the imaging team, of course, determined the shape, hence the volume. So you divide the mass by the volume, you get a bulk density, and it came out to 1.3 grams per cubic centimeter. Well, at this time, you know, asteroids were whirling rocks, and we were thinking more in terms of 5 grams per cubic centimeter. So this was a huge surprise. And it was Gene Shoemaker, with characteristic genius, who pointed out that the only reason that Mathilde did survive is because it's so underdense and so porous. If that were a solid rock, it would have broken up by any one of those 4 impacts. But the fact that it's a very porous object means that it can absorb the energy of the impacts, and it's the BB being shot into the styrofoam beer cooler analogy. And this shows the craters and how enormous they are. There's Mathilde, fairly large, 66 by 48 by 48 kilometers, the bulk density 1.3, and this thing was a paradigm switcher. The Shoemaker, or the NEAR Shoemaker spacecraft flew past Mathilde en route to a rendezvous with Eros, and it stayed in orbit around Eros for about a year, ending in 2000. And this is what it looked like from the orbiting spacecraft. So don't think of asteroids, near-Earth asteroids, as spherical objects where you can lazily orbit in circular orbits. You're going around something that's got an enormously diverse mass distribution, and your spacecraft orbits around it are going to have to take that into consideration. This is one of the higher resolution images of the surface a lot of dust on the surface, also a basketball apparently. We get the high resolution images when the spacecraft was coming down to land showed that the surface of this particular asteroid was covered with dust. So here are some of the details on the Mathilde and the Eros encounters. Mathilde was a C-type asteroid, bulk density 1.3. Perhaps that's typical of C-type asteroids. Perhaps. Porosity, very large porosity. Perhaps that's typical of C-type asteroids. Eros was an S-type asteroid. Porosity less than 30%. The bulk density about 2.7 grams per cubic centimeter. Perhaps that's typical for the so-called S-type or silicate asteroids. Most of the near-Earth object population are of this type. But you could argue that this type is actually more interesting because they're more primitive and more likely to have hydrated minerals that could be mined. I'm not going to talk too much about the Hayabusa spacecraft mission that was very successful in bringing back dust particles from the surface of Itokawa, because Paul Abel was going to talk about this later on today. But I'm just going to mention a couple of things. Notice the size of Itokawa compared to Eros. It's only about 500 meters end to end. So that's actually larger than the objects you'll be dealing with. So you're not dealing with very large near-Earth objects. This is the four sides of Itokawa. It's got two lobes, perhaps. At one point, it was disrupted by a collision, and those two lobes came back together to form a contact binary. Notice that the neck region between the head and the body is relatively smooth. Again, that's probably a gravity low where dust and materials settle back down. Notice there's very little evidence of any impact craters. Why is that? Well, on small objects, one impact is going to form a crater, but the next impact is going to cause seismic shaking, which will rattle this object, and it's like a tray of bread dough. You can fill in the earlier craters with a subsequent collision because of this seismic shaking. Most of Itokawa's surface is very rough, rubble-piled chunks and boulders with few obvious craters. It's not an easy object to land. I mean, the Japanese landed in the smooth area because it was safer there, of course. About 20% of the surface is very smooth and covered with small pebbles. And so here's sort of a summary of Itokawa. It's 500 meters on the longest side, rotation period of 12 hours. That's good. Bulk density 1.9 grams per cubic centimeter. It's an S-type. It has no extensive linear features, as there were on Eros, so it may imply there's no pervasive fabric. It's probably a rubble pile. Where's the dust? Well, there's about a 2-meter regolith of millimeter-sized particles or pebbles. Impact craters, probably erased by seismic shaking. The spectral measurements of Itokawa from the ground in spacecraft suggest it's an S-type or analogous to an LL chondrite meteorite, which is one of the most common types of meteorites that we pick up on the Earth's surface. Okay, so we have a new paradigm for comets and asteroids. Comets are weak and very black, icy dust balls. Surface collection of talcum powder-sized dust, silicate dust, about 30% ices, mostly water ice just below the surface. Fairly recent resurfacing and a few impact craters. Bulk density less than 1, porosity greater than 60%. Some evidence that on Tempel 1 does have a uniform composition, although there's more carbon dioxide coming out of the south than the north. All image cometary nuclei look so different that constructing a generic cometary nucleus is tough. I mean, these things defy our desire to put them in boxes and say, that's a cometary nucleus, that's an asteroid body. They're so diverse that it's difficult to do that. Asteroids run the gamut from wimpy ex-cometary fluff balls. Comets that run out of gas or ice are then, by definition, asteroids. So you've got some asteroids that are fragile ex-cometary structures. You've got some asteroids that are rubble piles, a lot of asteroids that are rubble piles. You've got some that are shattered rock, some that are solid rock, some that are solid slabs of iron nickel. So you've got the whole gamut from wimpy ex-cometary fluff balls all the way to slabs of solid iron. So the diversity is enormous. The problem is, without going there, we don't really know what their structures are. We can infer them from ground-based observations, but you probably need a precursor mission to look at your asteroid and understand it before sending humans. All right, 15% of the near-Earth asteroids are binary. There's actually 2 triple systems to date. 10% of the near-Earth asteroids may be ex-cometary fluff balls. They're a very diverse population, some binaries, mostly rubble piles. All of this was determined by scientists, astronomers in the 1980s and 90s, completely unaware that someone had determined all of this back in 1960. Who was that, you ask? Well, that was Donald Duck and his cousins Huey, Dewey, and Louie. This is a comic strip back in 1960. This is back in my day, not your day. But they came up with an idea that many of these asteroids are no larger than houses, and the oddest shapes. So the diversity of asteroids was there in their comic strip in 1960. Donald actually came out and noted that some of them were in orbit around others, and they even came up with the rubble pile structure. They're not even glued together, so there you have it. 1960, Donald had this figured out. Okay, in summary, why go to near-Earth asteroids? Well, obviously, one of the reasons you want to go is for exploration. They are stepping stones to the ultimate exploration of Mars. They would provide tests of technology, tests of radiation damage to the astronauts. It's a short round trip time that is much shorter than the trip that would be required to get to and back from Mars. Can astronauts live together for months at a time in a very confined region out of sight from Earth in a radiation environment that's fairly hostile? Would they wind up killing each other after a while? They might. Science, we mentioned that these asteroids are important from a scientific point of view. They represent the primitive bodies of the solar system. So if you wish to understand the chemical mix and the thermal environment under which our solar system formed 4.5 billion years ago, you'd like to study asteroids. You'd like to bring samples back and study them in the laboratories. Understand, for example, the deuterium to hydrogen ratios in the hydrated minerals or water ice that come from the asteroids. Are those deuterium to hydrogen ratios the same as in the Earth's oceans? And hence you could make the connection that these objects did indeed bring much of the Earth's water to the early Earth and allow life to form. I mentioned that they're important resources for building structures in space. If you're going to build habitats, then you're going to use the raw materials and the water that are already there. You can break the water down into hydrogen and oxygen, which is rocket fuel. So these objects could be the fueling stations and watering holes for the future interplanetary travel. So in a sense, these objects represent the future, and if for planetary defense, if we don't find them, track them, and deflect any Earth-threatening objects, we won't even have a future. So that's a summary, and I thank you very much for your attention.